but this is the decentralized deck room. So perhaps it would be cool to do like a 30-second small introduction of people. Ari, you want to go first?
Sure. Hey guys, my name is Ari Marder. I am a moderator here at the conference. I also work at Antenna Group, which is a marketing and PR agency for sustainable technology companies. So we do a lot of work in this space, and I'm actually particularly branching the company into carbon tech. We work in all sorts of alternative energies and the rest. I also am co-founder of a nonprofit, a volunteer nonprofit called the Open Air Collective, which Adnan is actually a member himself. We're working on a few different fronts. We have a lot of policy stuff going on the state level here in New York, and hopefully other state and municipality levels to help advance direct air capture and carbon tech broadly through different policies that will help spur investment and innovation in those fields. And we're also on the R&D front, building the world's first open source hardware direct air carbon capture machine. So that's a little background on me. We still got a little time before the official start, so let's keep going around. And then you want to pick the next person?
Yeah, let's just do it on the order here. Murray Domingo, you want to do a quick intro?
Yeah, I'm here. I'm actually one of the volunteers as well. Let's see if my colleague is here. Stacy Williams and I are actually two of the volunteers. We did some of the PR for this conference, and we're pretty tight with Ari and Tito in terms of their whole network and what it is that they're doing. That's my short version.
Awesome.
Thank you.
Okay.
Hi, I'm Sue. I am in New Jersey, and I just finished up a program at Columbia where I was able to study with Peter Eisenberger and Klaus Lackner. So that was very cool. And so I'm really into direct air capture and interested in finding out what people think are the practical ways of either using or disposing or storing the CO2 that's captured.
Okay, Jack Sullivan.
Hi, I'm Jack Sullivan. I am the chairman and founder of Red Carbon. We're a pre-seed stage startup that focuses on sequestration and use of carbon simultaneously above ground. We think it's a novel idea. We think it scales, and I'm here building relationships and trying to get to know as many people as I possibly can to help me push the ball forward.
Above ground as in aggregates, or like?
Call it carbon composites.
Cool, cool. Okay. Noah, learner.
Sure. Everyone, I'm Noah. I'm a current graduate student at Yale doing a joint degree program at the business school and the School of Environment, previously the School of Forestry. We'll be interning this summer for a growth equity fund that focuses on distributed sustainable infrastructure projects. That's why I was specifically interested in this panel, but have been interested in carbon removal, direct air capture for a while. So just excited to be here and learning.
Very cool. Eugene Chen?
I'm with the Anthropocene Institute. I work with Carl Page on evaluating different energy technologies primarily. Just here to learn more about what everyone's doing.
Cool. Yuren Wang? Let's go to the next one. Louise Hamdi?
Hello everyone, my name's Louise. I'm a postdoctoral researcher at Swansea University in the United Kingdom, and our group are currently researching polyamine-based carbon capture solid materials, and we're particularly interested in direct air capture, so this is why I'm here to learn about decentralizing DAC. Thank you.
Very cool. Xiaoyu Wu?
Hello everyone, so my name is Xiao Yu. I'm an assistant professor in University of Waterloo in Canada. I'm interested in direct air capture personally, and I would love to go into that direction in my research, so I'm here to learn more about it.
Awesome. Michael Leggett?
Hi, yeah, I'm an advisor at Nori. I'm just generally interested in any method of carbon removal.
Awesome. Love the podcasts. Christian Gubbs.
Hi, my name is Christian, and I just graduated with my bachelor's in chemical engineering from Washington State University. There I did a few research experiences, and one of them focused on CO2 capture and conversion, and that I'm hoping will be the focus of my graduate studies in the next 2 years. I'll be pursuing a master's degree in energy environmental engineering at the University of Sheffield in the United Kingdom next year, so I'm excited for that. It's a taught degree with a research component, so I'm hoping to find a research project there that has to do with CO2 utilization.
Ari Gentry.
Hey, I'm a co-founder at Negative. We're making consumer products out of atmospheric CO2.
Awesome. Let's see, Trevor Davis.
Yeah, hey guys, this is Trevor Davis. I'm an impact investor at a fund in Los Angeles called Trilink Global. We facilitate private credit investments in emerging markets. We're industry agnostic, and we invest across Latin America, Sub-Saharan Africa, and Southeast Asia.
Cool. Brian Seeger.
Hi, am I on?
Yeah. Yes.
Yeah, I'm a professor at DTU. We actually take the CO2 and do electrochemical CO2 reduction into products such as ethylene for plastics and ethanol for hand sanitizers. So that's why I'm interested.
Awesome.
You know about the Airco? They do both of those things.
What's that?
The Airco is a company that captures CO2 and turns it into hand sanitizers and vodka from ethanol.
Yeah, you're talking about Staff Sheehan's company?
Yeah.
Okay. Yeah, I know them.
Kai Fisher.
Yes, hi, nice to meet all you. I'm Kai Fisher, I'm co-founder of Positive Products. We do small-scale solutions, which is why I'm here. Currently, we use biochar as a base material to manufacture stuff, and on the last meters to finalize our biodegradability, tunability of our products.
Okay. So I think it's 11:15. I guess everyone's here. So yeah, I'm going to stop with the introductions. So we are talking about decentralized direct air capture systems. I'm going to talk a little bit about myself. I have a physics background. I'm a software developer. I have some hardware experience. And I'm very interested in direct air capture. I was looking at joining a direct air capture company, talked to a lot of direct air capture companies. And one of the things in that process I found out is that at this moment, a lot of entrepreneurs and researchers want to do something with direct air capture, but they don't want to build the direct air capture machine themselves because it takes a lot of time and is very complicated. And what I saw is that the current direct air capture companies are not suitable for smaller people. So for example, if you look at carbon engineering, they have very large scale, industrial scale solutions. And then Climeworks, their smallest unit is also actually very large. It's 2 by 2 by 2. And then you have like a tiny container with that. So I was thinking about what if you can create smaller direct air capture units. So the idea would be is to piggyback on consumer electronics that are very cheap and can be bought in high scales and high volumes, and basically use, for example, a computer van and use all these electronical parts. So the idea would be is I'm currently building a temperature vacuum swing direct air capture unit. That means that basically the way direct air capture works is you have this kind of sorbent. This sorbent absorbs carbon dioxide. And so for example, you could see like this sorbent and you're passing air through it. And then after a while, enough carbon dioxide sticks to it and then it's saturated. And once it's saturated, you basically bring it into a room and then you would add energy to it. That can be in the form of water that's evaporated. That would be moisture swing, one of the methods that Klaus Luckner does, or you can add temperature to it. So the process I'm interested in is temperature vacuum swing. So basically what you do is you have the sorbent, carbon dioxide pass through it, you bring it into a room, then you create a vacuum. Because you create a vacuum in that room, nothing else is there, and then you heat it. And once you heat it, the sorbent releases carbon dioxide and it releases water. So after that, if you want to process it, you could also split the water from the carbon dioxide, and then you can compress it, and then you've got pure carbon dioxide. Or you can use the mixture of carbon dioxide and water and use it in a setup where you can have a lower concentration of carbon dioxide. But the basic idea I want to talk about is that I personally think that a decentralized direct air capture unit can actually be scalable and can be a cheap solution, because everyone's working on these large devices. But if you look at it from this standpoint and look at the cost of the equipment, then if you build this tiny unit, you actually have a very low cost by default, because all the components are off the shelf. And then the other interesting thing is my device will be low voltage, so you can directly couple it to solar, for example. So that's a quick introduction of the idea of how we can use these cheap, decentralized direct air capture units to empower a next generation of entrepreneurs and researchers.
I don't know. I think that's really interesting. I think one of the things, Jack, you asked this or you mentioned bringing up decentralized should scale better, and I think you're exactly right. It should scale better. I think of like adsorbents, like what Mosaic Materials has invented, and like why shouldn't it? But Adnan, to your point, you said something that would plug into a smartphone. I don't see why 1 foot by 1 foot or 2 foot by 2 foot would be a problem. You know, we all have well, most of us have dishwashers or something like that, or something you could fit into your backyard or up where your weather vane is, where there's a lot of air exchange. I don't think you'd need to power air through. That's how I think of small decentralized direct air capture. You get a homemade or off-the-shelf box, and then you add in a commercial adsorbent from one of these companies that's developing them. Just be interested to hear people's thoughts on that.
Yeah, for sure. So I looked at the energy consumption. The energy consumption of the computer van doesn't add too much on the whole part, actually, but you could also try to get as much energy as possible passively. One of the ideas probably will be my first product to market would actually be a sorbent cycler. So I'm talking to one of the universities here. I'm from Amsterdam, by the way. I'm talking to one of the universities here, and one of the problems at direct air capture is basically sorbent cycling. We don't know how stable sorbents are after 1,000 cycles. So if you can have like these very small direct air capture unit, then you can test a lot of cycles and a lot of different sorbents in a very cheap method. So to answer Brian Seeger's question, I don't understand why small scale is better. Typically you get benefits in scaling things up. Well, it's actually, you're already piggybacking on a scaled up infrastructure, since all the parts you're using are already scaled up. So if you look at a computer van, it's scaled up. If you look at the heating system I have, it's already scaled up. If you look at all the different systems to move the sorbent, etc., those are all, you can already buy them at scale. So the reason why it's actually cost effective is because all these parts are already made on scale. Let's see.
It's also, I'll just add while you're looking at the questions there, from our experience at Open Air with building these open source miniaturized DAC units, and we're just for record, we're probably a month out from building the first one, but one of the advantages we see in general for the industry as a whole is that whole innovation cycle gets sped up rapidly, right? Like these utility scale size ones you'll see from Carbon Engineering and the like cost $3 to $4 million just to test them out. So if you have a version that's this big instead of that big, and instead of $4 million, it costs $2,000, you could start getting a much faster cycle of innovation. And then if you do plan on scaling it up, you now have you're 10 steps ahead. And then you also open up the door to, if you're going an open source model, then you can now, it's accessible to now thousands or millions of people to jump in, and you can have more residential applications, like fill up your soda stream with the CO2 out of the sky kind of thing.
So yeah, to add to that, so one of the questions here is how do you capture several tons of carbon dioxide, and where do you put the several tons of material? So my idea is actually that the machine that I'm building is or an open source machine will empower a lot of new entrepreneurs who would think of the next products that you can make of it. So for example, if you're an entrepreneur now and you want to do something with carbon, then the smallest direct air capture that you can buy is the one from Climeworks, and it's actually very big. But let's say you want to test out and create, I don't know, tiles that are made from carbon dioxide out of the air, or you want to create a protein made of carbon dioxide out of the air. At this moment, if you want to do that, you also need to figure out that part. But what if you could just buy this machine that's very modular that you can hook up to solar? Then you could create remote protein, for example, for military purposes. You could create protein out of the blue, out of somewhere, so you don't need to transport food. So the idea would be, with this device, to spark a new innovation and ideas of what we can do with this carbon. So for example, what I would be very interested in is creating graphene out of carbon, because if you could create graphene out of carbon, out of the air, then you can create carbon wherever you want, and then you can create carbon at the cheapest price of electricity. So for example, you can go to the desert, and if you can just then create this machine that just continuously creates carbon, then you just put it there and just creates carbon, and you've got these like machines that just drop out carbon. So another way would be if you could hook up this to in the desert and then create fuels out of it, because it's intermittent. That's the whole beautiful idea about this small scale, low voltage direct air capture unit. But I'd be interested to hear, like, if you hear this idea, what kind of ideas would you have? Like, what would you do with such a unit? Would anyone be interested in such a unit?
Are you opening it up to the floor?
Sorry?
Were you opening it up to the floor, or was that just for the
power? Yeah, no. Just jump in. Like,
yeah, I mean, I think from my own personal point of view, I think the economies of scale are perhaps seen in the wrong way. Making things small is not necessarily about using them at a small scale. I mean, if you look at things like batteries, or cells, they're stacked into arrays to form batteries. So, you know, the way I would look at this is, if I could, and I actually gave this advice to Climeworks. I went to Climeworks and I was like, what are you doing with this? You're making these huge, complicated machines. Everything's bespoke. I would containerize it, even at the expense of extra energy costs, and then just make them in a factory that just spits them out all day, every day. When they break, you pick them up on the back of a lorry, you bring them back, you just send out another unit. It becomes carbon as a service. You're not selling a physical product, right? And you might find that the average customer installed 2,000 of the units. But the point is, because they're modular, replaceable, disposable, you put in 100 of them, 5 of them break, who cares? It doesn't matter. You'll pick them up on Wednesday, right? It's just a different way of thinking about it. If you think about how companies like Facebook have done this, and particularly probably the best example is Amazon, where they just take generic hardware and they just cut the cost, and they put the most slick service layer on top of it, so that you just don't know what's you order a server, you have no idea where it is or what's running on it. You just don't care about all that, and it just works. And doing that with carbon machinery, I think, is absolutely critical. And as the technology improves, you can go from the sort of Byzantine technology of carbon engineering to the more modern sorbent type technology from Climeworks, and then on an ongoing basis to electro swing, which I think is likely to replace all other technologies, because you don't have to have a heat source or anything mechanical to do that. And as you go down that development path, the customer doesn't know or care how this is all powered and what goes on in that box. All they know is that it produces 5 kilos of carbon dioxide an hour, and it costs them $300 a month.
Yeah, exactly. So one thing to add to that. So one of the things that worries me if we do direct air capture, that we might not do the same things, that we might end up adding more carbon instead of less. So one of the things to counteract it is I thought of also adding a CPU to this device so that it actually is a carbon accounting machine. So basically what it's doing is it will do a life cycle assessment. It will basically know, like, okay, this direct air capture unit has been made with these types of upfront carbon emissions. Of course, the more you improve on that, maybe you can even make a carbon negative machine by adding insulation that is carbon negative, etc. But then you know where it will be shipped to, you know what the emissions are. And if you hook it up to the grid, you might be able to get the live emissions from the grid. And then you can create this carbon accounting machine so that also for governments, it will be way easier to say, like, hey, this machine or this action or this entrepreneur with this ID is doing something good or it's doing something bad. You know, that's also something that should be visible in the system. And the cool thing is, yeah.
Just to expand and extend on that, I mean, I think one of the things that people don't at the moment think of these carbon machines as being a critical provider of is drop-in loads for energy systems. And one of the ways that I think these machines are going to work well from an economic point of view is to be able to switch them on to either, in some cases, if it's electro swing, sub-second, and with some other machines might spin up more slowly. But the idea of basically being used to replace curtailment on the grid, because curtailment, particularly of distributed solar, is really expensive. And these machines have got terrific energy consumption, and you can switch them on very quickly. And one of the ways that customers can benefit from those is by having stacked services based on being able to either assist in energy arbitrage, so you're just shaving demand a bit at higher supply times, so that that you're buying energy cheaper. But you can actually be in a situation where the grid will pay you to take energy away if you can switch your load on really, really quickly. And from a consumer's point of view, the economics potentially can be very strongly affected by having these droppable loads that you can just dump into the grid whenever you want. And if you kind of think of a period in the middle of the day, like, it gets down to kind of individual clouds going over individual solar farms, and you want to be able to switch on, 500 direct air capture machines in sub-second timing to make sure that your grid is kept stable. And that service is very valuable, and grids will pay a lot of money for that. And people are just not talking about that yet.
So there's one problem for that, is that your CapEx are heavily tied to the amount of hours that your equipment is running. So here also it matters if you can create your unit upfront cheaper, then your CapEx are also way more favorable. And I actually think from a lot of points, using these smaller units is beneficial. If you look at the life cycle assessment of such a unit, if you look at Climeworks units, these are aluminium boxes. The upfront carbon emissions of aluminium boxes is very high. So by creating these smaller, simpler units, you can actually improve the upfront carbon emissions, and you can also improve the cost efficiency of these units. Yeah.
So I have a suggestion that a crypto mining data center could use the waste heat to produce carbon, and that excess waste heat would actually be contributing to the value of that that mining process by accumulating carbon credits as well.
So then you would say, so you could turn it the other way around. You could put a CPU inside of a direct air capture unit and use the waste heat. That would be the idea, actually.
I think so. Yeah. I think a lot of crypto mining people would really be in favor of neutralizing their footprint on the grid.
That's interesting. So one interesting idea also I saw with from Kai Fisher. Basically, Kai said you can also hook this up to 3D printing, and then you can have remote 3D printing, because you would then have a 3D printer with some solar panels, and then take the carbon out of the air and then print stuff with it, and you can do it everywhere, and you don't need resources. So I think that's also a very interesting use case. Yeah, please just drop in with questions. I think it's just an open discussion. So
just to expand on that idea of the 3D printing use, I mean, a much more obvious use, and this has been kind of trial, but there's no integrated system provider, is to have e-fuels, just off-grid e-fuels. So say, for example, if you've got a rural farm, right, where you might have some waste heat from a biodigester and you've got a grid connection, but you don't want to be buying in diesel, it might make a lot of sense to just have your own little diesel plant that sits on your farm and powers up your heavy plant. If you've got waste heat, if you've got a grid connection, then that becomes a very sellable service or a sellable product to have that unit that is an all-in-one integrated machine. And you've got people like Sunfire, I think it is, that does that, but I don't know
Germany
solution provider that integrates both of those systems and ships them out.
So one of the issues that, if you look at the way currently, for example, Climeworks wants to do synthetic fuels, is that they have like a lot of different companies doing all those different parts. So the integration between those services is not very good. So you lose a lot of efficiencies. So there's actually a Dutch company, they're in stealth mode, but they're from my alma mater university. And they are trying to create these decentralized direct air capture units that produce ethanol inside of, or methanol inside of the desert. And they have a super interesting integration of all these different components. I'm seeing one discussion with Brian Seeger. Basically, any electrochemical carbon dioxide extraction will be wet. So I'm not sure what you mean with that, but basically the way the temperature vacuum swing works is you have the sorbent. Sorbent can be a primary or secondary amine, and air runs through it. And then you, once it's saturated, you take it inside a room, you enclose the room, vacuum the room, and then you add heat to it. Once you added heat to it, carbon dioxide and water is released. So in that part, it is wet, but, and then if you want, you can separate the carbon dioxide and water by different types of processes. You could condense it, for example. So this process would actually create water. If you want, in some certain cases, you could get that water and use it for hydrogen production, for example. That's what the guys from TU Delft do, the other guys that do decentralized direct air capture.
Can I just expand on that methanol point you made? Because I think methanol is really interesting. I went to a seminar in Houston about this, like a 3-day conference on you know, it was mainly oil men coming to this thing, which gives a really interesting perspective, because most of the people that I talked to are academics and tree huggers, and almost all of the people that there were talking about methanol as an intermediary step. And I think one of the most interesting things about methanol is that you can use it for alum cycle combustion. So you can, in the daytime, when you've got a lot of solar on the grid, you can clip off the excess solar. You can make that methanol chemically using carbon dioxide that's been captured out of the air, and then electricity. And then you can store that methanol either for surface transport, and that's quite big in South America, where they've got a lot of fuel blends that involve quite a lot of alcohols in their fuel blend, mostly from biological sources rather than chemical sources, but that's by the by. But the advantage of the methanol fuel is if you want to use it as a fuel to get you through winter highs where you've got very cold temperatures and very little wind, where it's very, very difficult for renewables heavy grid to get you through, then it plays very nicely in storage. You can store it for long periods of time. It's not It's pretty stable. It's not polluting if it escapes in small volumes, unlike oils. And you can burn it in an Alam cycle engine and recover all of your carbon dioxide. So you don't have to go through the cost of capturing the carbon dioxide twice. And you can either then reprocess that into fuel if you can store it, or alternatively, you can just inject it into the ground. And I've got a paper coming out, hopefully when I get around to writing it, detailing the energy implications of that particular fuel cycle.
Yeah, definitely.
Just to actually build on that a little bit, with regards to the CO2 and the hydrogen to methanol, that's actually a pretty well-known process, and that's not that hard to do at all. So it's relatively straightforward to do that.
So I've got another question to the floor. Is anyone working on a process to create solid carbon out of carbon from the air or concentrated carbon sources?
Yeah, there's a company called Solid Carbon that does it, and they make a variety of high technology carbon forms to use for high tech industrial engineering, basically.
What's the end product they have?
I think they make a variety of things. So they make equivalents of basically like carbon composites that you might get on high end vehicle components and stuff like that. But I'm pretty sure the company's called Solid Carbon.
Okay. And
there's also another company that makes carbon nanotubes. I believe they were in the Carbon X Prize. I can't remember who that was.
C4CNT, I think.
Yeah.
So,
is it Stuart Lick that was leading that?
I don't remember. He's a professor.
He's
I don't
definitely
remember.
involved.
Yeah, I think it was Stuart.
It was him.
That is, yeah, I think that is very interesting, because if you can do that, if you can sell graphene as a feedstock, the price is very high, and like it makes sense. You put it in a stable form, you can use it for batteries, etc. So I think that's a very interesting development, but yeah, not a lot of people are working on it, unfortunately, I think.
So this is Shannon Fiume with Open Nanocarbons.
You're working on that, right?
Yes, I'm working on that. Unfortunately, it's so progress report on working with the graphene part. Graphene is so, the magnitude size difference between going from graphene to bulk carbon is so huge, and even to CO2 eventually, or going from the other way, from CO2 all the way back to graphene, is so huge that it's not, I don't want to say it's not possible, it's just unlikely that graphene or premium carbons would be the answer. Definitely in a portfolio, it would be a small premium niche in anyone's portfolio, but it just doesn't look like any of the way the volume plays would work for like just making some kind of bulk carbonate. Like if you're doing concrete or whatnot, you're just manipulating a carbonate and trapping CO2 that way. That's much more easier than say going to pure carbon. So open nanocarbons, definitely the research right now has been on hold a little bit, doing a bit more background research into kind of sizing and scope, and also figuring out, well, how fast and how much carbon do we need, and kind of how fast do we need to go to really get us away from hitting the tipping points and whatnot. So that's kind of been taking me a step backwards from actually doing the practical, more science and engineering of, well, how do you pull it apart?
I missed a little bit part of that, but I'd like to connect with you later on that. But one of the interesting discussions that was in the previous breakout room regarding advanced nuclear combined with direct air capture is that that might actually be an interesting combination there, where since the advanced nuclear, the molten salt reactors have a high temperature, like 600, 700 degrees Celsius, maybe in that environment, you can actually create graphene.
Anything that gets, you probably have to go a little bit higher is it only 600 Celsius for the
No,
moment?
they can up it with electricity up till 1,000.
Okay.
Yeah. Japanese high temperature test reactor goes well above that. That's an extant reactor, and that's already a relatively large scale. I think it's shut down now, but I think
process?
that was working. It was somewhere between 9 and 1100 centigrade. I've got a paper coming out on this, but I can't remember the figures because I submitted it ages ago. But that's the hottest reactor that works at the moment. Molten salt reactors and lead fast and sodium are potentially able to go up to pretty high temperatures, but you know, around or above the calcining temperature, depending on the technology. But I haven't looked at using those to produce graphene and graphite directly. I've only looked at using it for the calcining step.
Yeah, which also makes sense.
But there's been some pretty interesting work on it because people are all over small modular at the moment, and there's been some new materials breakthroughs that are pretty much the first materials that have been approved for like 30 years to use in nuclear reactors, and they're pretty critical because they're enabling steps for these high temperature reactors that will enable, you know, the high temperature processes such as calcining or other chemical processes that require the high temperatures to be made, because you've got the alloys and stuff that can support those reactions, whereas previously they're just genuinely hard to make reactors that are capable of supporting those high temperatures.
Right. I think it's anywhere.
Yeah, sorry, Shannon.
I think it's anywhere between 700 Celsius and upwards to about 1400 is kind of the range of, and the low end is biochar, and then it's, if you have assisted ways of making, there's specific ways you can do it in the low temp for graphene synthesis, and then higher temp it's a little bit easier.
So
but either one would work.
That's actually a really good case maybe for yeah, advanced nuclear reactors. Pretty cool. Okay.
Yeah.
Can I ask a question of one of the fellow attendees?
Yeah, go ahead.
Christian, I'd love to hear any thoughts you have on distributed.
You're talking to me?
Yeah, you there? I'm calling you out.
Yeah, no, I'm here. I think that's an interesting idea. I read an article from Nature Communications that was on, it was called Crowd Oil, Not Crude Oil. And basically they were fitting AC HVAC systems with CO2 capture and then converting that into fuel. And they were saying, oh, this could be something we use in the future. And they were doing it in large office spaces. So there was actually a significant amount of CO2 being captured and utilized there. So I think it could be a potential option for sure.
I'd like to make a comment. What Christian said is right, and I read that same article. Somebody put in the chat link something about Hypergiant. They have an EOS reactor which hooks up to your HVAC, but it's a wet system. So then there's a question of maintenance and how you get everything out and processed, and turns into a management problem. I also heard something on the Nori chat that discussed hooking up to an HVAC system in a distributed way, which was also very interesting. The advantage of an HVAC system is the air processed is 400 times direct air. So you can capture a lot more carbon a lot more quickly, so it's efficient. But I fear that if we're trying to scale it rapidly in a distributed way, it can't be wet, which is why I asked that question in the chat. I think if it's wet, then it's a distribution problem, right? You'd have to service those systems every month, and then you need a service force globally that just gets too big. You can't manage it. So if it's dry, hell, you could put it in the mailbox and just ship it USPS to a central facility. And then the central facility can just receive a whole bunch of carbon. You can just leverage the existing postage infrastructure if the systems were thin enough to fit through the postage systems. So there's something there. I don't have the answer. I think distributed is barking up the right tree because I think it scales rapidly.
Yeah.
If you can figure out a way to do it in a dry process.
Yeah. So I can only build when you're talking about HVAC specifically. We talked about a bit in the chat, but Clean O2, which is a company that does the CO2 capture from HVAC units, So what they do, they're doing more on like commercial buildings and buildings where it's not just a small house you're dealing with. And they already have people coming in on a regular basis to do maintenance checks. So what they've done is they're training those people who are already doing regular HVAC maintenance checks, training those people in the basic means they have to do to switch out whatever it is, make sure that's fine, and take the carbonate that the HVAC unit has produced and replace it with a new bag. So that's how they're scaling. There's obvious limitations with that model too, including making sure that there's whatever. There are obvious limitations to that method.
They're called Clean O2.
Clean O2. I can. They're Clean O2. I can put their link.
I'll check them out, but I worry about the scale of the maintenance component.
Yeah.
Right? And it just doesn't scale. Let's just be frank.
Right. So
we're trying to figure out the problem quickly. It's got to be something that doesn't require a lot of maintenance or doesn't.
Right.
That's why, if we can find a way to create a solid product out of it, then you've solved it, because with decentralized, you can scale it and you can put it where the energy is cheapest, and then, you can put it everywhere. But if we can find something that creates pure carbon, then we're in. But the question is, what is that?
If you can separate the oxygen from the carbon in a distributed box and locate it wherever, hell, you could give them away.
Exactly.
Right.
You can just
get credits, right?
Yeah. Once you get the carbon, then you're getting paid by the governments around the world to sequester it. You can start giving some of that off as dividends to whoever agrees to put one of these fans in their house.
So the biggest, and that's the whole issue. Like, I feel like no one's working on this specific problem. Like, there are some people working on it, but not enough people are working on this specific problem. If we solve this specific problem, then we can scale it.
Yeah. I think this may be a silver bullet, but the technology isn't quite there yet, or the material scientists haven't figured it out yet. And once they do, then somebody's got to build the infrastructure to manage it.
So from what I've seen, I'm sorry, Jack, I didn't mean to cut you off.
No, go ahead.
I've seen it's able to do it physically. Like, when I've spoken to companies who have gotten DAC at this scale, the issue was more the economics of it. It didn't work out. So, I mean, that's kind of what we're doing at Open Air. We're a nonprofit. This is just open source research. We don't care if the economics don't make sense at first. And the goal is you innovate it to an extent where the economics do make sense for it. And then you're opening up this door, kind of what we just touched on at the end there, of we talked a lot in the chat about having models to do the collection side, right? And that's if the business model is built on collecting that they aggregate whatever you're getting as the end product there. But there's also going to be a huge market of people who want to just have one of these machines in their house if it only costs $1,500 to get it. And if they can leave it alone and that's it, and then I mean, there's still things like, what do you do with the physical product at the end? But if there's a way for them just to keep it, then you're done. You're just selling the machines, and that could be a business model in itself, especially if you can scale up this manufacturing process for that.
I think there's a viral component to this. You create a distributed box that people can receive in their homes and even get a dividend from if they accept the box. They don't even have to accept it. You just mail them out, and if they don't want to do it, they throw it away. Otherwise, they plug it into the wall, and it runs, right? I mean, then it's a matter of collecting whatever they're capturing and figuring out a way to get it to a central component where it can be processed. And then I think it's maybe leveraging the postal system and figuring out a way to do that. But if you can come up with that,
so
then maybe it scales to 1 billion people, and everybody gets one of these things on their desks, and you got 1 billion units. You can mass produce those rapidly over the course of a couple of years.
Yeah, to add to Clay, just ask your question there. It's fine on the floor. But
I'm done. I'm just gonna jump in. Let you guys know we have like 5 minutes. We're gonna have to.
Because we're talking about decentralized DAC, and I think Clay's question is correct indeed. So you just ask right away. Like, you're interested in, just ask your questions.
Yeah, so it sounds like there's a lot of issues that we're kind of glossing over around the maintenance of it, around moving the byproducts. I really like the idea of having these little tiny devices that individuals can purchase, but are we having them distributed just to have them distributed, or does it make sense to just have people buy these like storage containers and they just live in a centralized location.
Yeah, I think I'm personally not the hugest proponent of putting them inside of people's houses, but I think building this small machine does have its benefits, because you can still like put large fields of these machines next to each other. But I think just the sheer act of having this small component that uses off-the-shelf components is like the thing that where the economies of scale already kick in. So I think that's the reason why the small scale direct air capture can be very cost efficient. So, and I'm not sure about the placing it in people's houses, to be honest.
Yeah,
But
for me, that's almost I come from a marketing background, and the excitement I think that would be generated around being able to have a machine that's literally reversing climate change, I think would generate a lot of interest, a lot of media attention, which will bring more investments into the space, there's a lot of secondary and third effects that come from that. And then there's more money in it. So now there's more investment in the research and development, and you'll start building from there. So the distributed model in itself kind of has an advantage on that stage, as long as it's something that you can afford to buy.
If you want to put it in this marketing angle, I think one thing that would be interesting, and also from a life cycle assessment point of view, is if you could create proteins out of it. So basically, people could create their own artisanal proteins. So you would have your own vat with your own bacteria that would hydrogenate and then create protein out of it. I think that would be at least interesting. Then people could maybe create their own lab-grown meats, you know? So that would be a possible consumer angle there.
Air protein does that, I think.
Exactly, but then you would be doing it in your own home, and then you don't need to buy like a part of your diet.
One of the things that we discussed earlier was kind of the solar panel model. I know in California, they kind of have solar panels that push electricity onto the grid. And I understand like the benefit being that, well, now your solar field is distributed. You don't have to worry about clouds completely taking down your whole system. But for something like this, like you just put them, you might as well just put all the devices in one location. And then you can have your protein development, and you can have your nanotubes, doesn't matter, so.
Yeah, agreed on that, yeah.
Question about the proteins, and I don't know the answer. I fear that a lot of the use cases that are being proposed don't sequester the carbon for more than a couple of years. And I worry about that. So I fear that whatever use case we settle on, or whatever use cases get adopted and taken up, that they sequester carbon for a long time. Otherwise, we're not really solving the problem.
So if you're talking about if you're talking about air proteins, there's actually the way you would, George Monbiot, a famous writer of The Guardian, wrote an excellent article about solar foods. The way you should view these air proteins is, because you now don't need animal agriculture, and basically like 70% of the world, now 75% of 60% of the world is all based for animal agriculture. That means that you can free up the world and you can plant trees. Basically, you free up land and you can use that land to store carbon. So in the case of air protein, you do actually create the space for negative emissions as a side effect.
I think you, at this stage in development of the industry, you've got to look at it in a completely different way. This is not about delivering carbon sequestration. That's not the important economic event. The important economic event is driving down the cost of direct air capture. Because if you think about how other revolutions have happened, it wasn't the $1,000 mobile phones that changed the world and made African herders have mobile phones. It was the scaling of those mobile phones driving down the cost curve. So these edge case applications that are very expensive, just having more and more and more of them driving down the cost curve, so that you then get $30 smartphones in supermarkets. That's where the revolution comes from, because once it becomes that cheap and that ubiquitous and that reliable, just like all these throwaway products from biros to toothpaste tubes that we use every day, then that's what makes it possible to do sequestration at scale. You don't need to sequester in your kind of first 1% or even 10% of your applications. It's the other 90% that only becomes possible because you've driven the cost down, and that's what drives the economics.
I'm gonna add on. You can answer this last thing, and then we're gonna actually jump back in a second too. But those were really almost good points to end on. If you want to do anything like closing to wrap up, I'll post the link to get back to the original Zoom in the chat, and I can share my screen. Or that Zoom link will work just fine if everyone can access the chat.
Okay.
Ari, is the link you posted, is that what we mostly have been talking about, or is that a separate initiative, the Open Air Collective? I'm
sorry, that's my nonprofit on the side that we do. That's the open source, the research and development side, the link I posted there. Yeah, I was just putting that in case people are interested, and I don't want to shamelessly plug my own.
No, not at all. No, that's awesome. Plug away.
So basically, there are a couple of people working on these small modular direct air capture units. Ari has the Open Air Collective, which I'm also helping a little bit out on. I am currently still a little bit in stealth, working on my own direct air capture company. There's another one in the Netherlands, also doing these very small modular direct air capture units. And besides that, I don't know of any so far at this really, really small scale.
And I'm also, by the way, I'm on Slack, and I can post my own email here if anyone wants to chat about any of that more.
Yeah, me too.
Real quick, I did hear about a distributed research being done in Germany, and I heard about it through a Nori podcast. Now, I can't remember the academic who was doing it, but apparently he'd been working on it for a couple of years, and it was an interesting podcast. Check it out on Nori for their podcast. I'm plugging them, but they're a great source of information. And it was a German scientist doing distributed air capture through HVACs. Yeah, worth checking out.
All right, guys, I'll repost the link one last time in the group. Let's jump over. Thank you guys so much. Thank you, Anna, for running this, guys. This was a super enjoyable, insightful conversation.
Thank you, everyone. It was super nice, super fun. Yes, thanks.